Today we're talking about mechanical waves. So we just covered periodic motion, and now we're going to extend some of those concepts to waves, and we're going to develop the mathematics and the physics behind waves. Waves of this sort, or this sort, where they're more spread out, and then it's more dense, and then it's more spread out, and then it's more dense. So before we get into it, I want to kind of motivate this topic a little bit more, because in this lecture, we're going to mostly be talking about waves along a string, sending a wave pulse along a string, so a literal string. And if you just imagine a string laying on your porch or something, and you lift it up and you put it back down real fast, you can send a wave pulse down it. Or if you lift it up and put it back down regularly, you can send multiple waves down it, and you can have periodic waves of a periodic nature. So on its surface, that seems kind of like this is a heck of a lot of effort for a very specific niche little system. Why is there a whole chapter just dedicated towards how a string behaves when we mess with it? Let me see if I can illuminate why this is such an important topic. So waves show up everywhere, and they get much more complex. Sometimes, actually, literally, if you go far enough in physics, you get complex mathematics with imaginary numbers and such. But so wave natures of things don't just apply to things on a string, but if we study at an elementary level the mathematics and the physics of how waves behave on a string, it will serve us, it'll serve as like a good foundation for later elevating that to the higher complex systems. So there's basically, there's an end goal of eventually giving you the tools to describe many systems just by using a string as the vehicle to get there. So this is not a whole chapter devoted to how a string behaves, even though it may seem that way. It's a whole chapter using the way a string behaves when we perturb it as a vehicle to help you develop a fundamental understanding of waves in general. All right. So with that out of the way, by the end of this chapter, we're going to kind of get into normal modes, and that's really one of the things that shows up it shows up in my research. It shows up everywhere at a really high level. And so hopefully by the end, you'll be able to kind of picture, I'll give some examples at the end, you'll be able to picture how versatile these concepts are. It goes beyond just string. So this chapter, mechanical waves, you've already taken physics 2, so you know that there are electromagnetic waves. These are different. These are mechanical waves. They travel through a medium. EM waves don't need any medium to travel through. And so what we're mostly paying attention to are two properties of the wave. We're going to talk about its energy and how that propagates from point A to point B as the wave moves through. And we're going to talk about the displacement of the medium. And so that would be up and down or left and right as the wave passes through. These are the two key quantities that are important for waves, because it's really the two main things that waves do, that mechanical waves do. So no mass is transported from A to B. So if I have this string and I lift it up and put it back down, so I have this wave pulse that's traveling this way, the particles along it, as the wave gets to each particle are going to be moving up and down, right? So momentarily, a segment of string is going to be lifted up and then placed and then dropped back down. That's the displacement. Notice that the displacement is completely vertical, while and returns to back to where it started, while the wave is propagating to the right here. So the energy in this example is moving along to the right. I guess that's a different color. The energy is moving along to the right, whereas the displacement is up and down. And what's more, the energy goes from, we'll say point A to point B, whereas the displacement of the particle, like at a later time, this guy here is going to be moved up, and then at another later time, it'll be moved back down. So there is no mass that's going from point A to point B. That's not happening. It's just particles are displaced from where they were, and then they're put right back. But through that process, energy is transported from one place to another. So it's kind of a mysterious thing. You may kind of have an intuitive understanding of how waves transport, because we see them every day. But if you actually kind of think about it, it gets kind of funky thinking about how this actually happens. So we're gonna dive into that. Before I close this video, this section, I'm gonna say that there are two different types of waves, mechanical waves. There's transverse waves, and these are the types that I was just talking about, where you have displacement this way, while the wave is propagating this way. And so the propagation of the wave is transverse or perpendicular to the direction that the material is displaced. So that would be like a wave traveling down a rope. There's another type, which is longitudinal. Longitudinal waves are like sound waves. So sound, let me draw up this system here. If you have, well, actually, I'll just use this picture up here. So in this wave here, it's propagating this way. Each one of these disturbances, they're regular disturbances, they're traveling to the right. The particles, if you can imagine time going by, and these disturbances traveling forward through subsequent slices of the air, I guess we can think of it as. Each one of these things is going to be moving, each one of these lines, which represent air pressure, density of the lines, they're going to be moving left and right, right? And so the displacement of the material is in the same direction as the propagation direction of the wave. They're both to the right. And so that would be a longitudinal wave. So that means that the displacement is that way, and the direction of propagation is in line with that. So you might think, well, Joel, that violates what you just said. You said that there's no mass being transported. That's not true. So mass is going along that same direction, yes, but it's momentarily moving to the right and then moving right back to where it started. So if you just consider one wave pulse going through, let's say you have regularly spaced things here to start. Imagine those all regularly spaced. Then you send some compression through. So let's say you have some piston or something that pushes forward. So that compresses this area right here, and the rest have not felt the disturbance yet. So that means that these all have moved there. And then the piston goes away, or moves back, I guess. And so then there's regularly spaced stuff here, And the wave begins to propagate that way because each particle influences the next. And so now you have these nice butted up against each other. And then the rest have yet to experience the disturbance. And so on. So the wave propagates. And so if you look at each individual particle, let's say this is 1, 2, 3, 4, 5. So 1 and 2 and 3 are all pushed up next to each other. 4 and 5 are still there. But then over here, 1 and 2, they've moved back to their original place. And 3 is back where it is too. And 4 has advanced forward, right? And so particle 1 and 2, it kind of took this, it went forward and then it went back path, right, through time. So there's no actual mass being transported. This pocket of air is not propagating with the wave and ending up way over there. That's not what happens. So there's no mass transported. There's just energy being transported. All right. So it's also possible to have waves that are both transverse and longitudinal. It's kind of interesting. You can actually make a rope do this, I guess, if you're really skilled. But ocean waves are of this nature, and the water molecules actually travel in a circular motion as the wave passes through because there's kind of a compression underneath this, and there's also this, so this would be longitudinal down here, and then there's a transverse component at the top that goes up and down, and so they experience both, and so they end up moving in a circular manner. And one last concept before we end this video, the wave speed. So the wave speed is very different from the particle speed. So what do I mean by that? So in this wave up here, going back up here, the wave speed, which we use the Greek letter nu, so it's kind of a curvy V, that's the speed that the wave is propagating from left to right. That's very different from the speed that the particles, this particle, say, moved up here and then back down. Those are two distinct quantities. They're not the same motion. And so we have to keep those two concepts separate. There's wave speed, and then there's particle displacement speed, or rate. And that ends this video. So next we'll talk about periodic waves. So we're going to kind of put our previous lecture topic together with this one.